All right, everybody, we got to get through the last little bit of alpha carbon chemistry, and then we're going to move on to amines. But there is still a lot to do in alpha carbon chemistry. So let's get started. We're going to talk about a lot of different reactions, but at the end of the day, we're going to be talking about essentially enolates again. And there's not going to be a whole lot of things that, at this point, I don't think there's anything now that we're going to be talking about that isn't done via enolate. So let's get into it. Start up my machine here. All right. Let's see how it goes. All right, so we have talked about Aldol condensation. And so Aldol condensation, recall, was when we take an aldehyde or a ketone that has, and the bottom line is that it has to have alpha protons, and we form an enolate, and that enolate attacks the carbonyl group and forms a carbon-carbon bond. Now, depending on how that works, whether or not we follow that treatment up with heat or not, we can get an alpha beta unsaturated, or excuse me, we can get a beta hydroxy ketone, or if we follow that up with heat, we can then get unsaturation happening here at this position and do the actual condensation. So there's two types of aldol reactions. Up until this point, though, what we've done is we've limited our conversation to, if you notice, these two things are the same species. And so one of the things we're going to have to be able to consider for synthesis is what happens if we don't have the same species. Ultimately, we're going to have to figure out which one to make into an enolate and which one is going to be doing the reacting. And so let me give you an example of this. Let's go ahead and take one of the same species, but let's change up the other one. Let's make it have 3 carbons. And so let's take a look. If we put these two things in a pot and do a aldol reaction with it, then there's actually 4 possibilities. Let's just call this A and B. In the case where I get A plus B together, now I'm going to say that in this case I'm turning A into the enolate. So whatever I list first will be the enolate from this point forward. Then that means we would have a hydrogen here, a doubly bond oxygen there. We would get the reaction at the carbonyl group here, and then there would be the 1, 2, 3 carbons attached to it. Okay, that's A and B. What happens if I get, in this same pot, it's certainly possible for A and A to get together. What happens if that is the case? So let me make sure I'm doing this right. So if that's the enolate, it reacts there. And then I've got 1, 2, 3, 1, 2, 3 carbons. And this is the bond that gets formed. This are the 2 electrons in that bond. Okay, so now let's get A and A together. So I'm going to still make A the enolate, but it's going to react with itself in this case. In this case, there's only 1 other carbon. So that's a different product. That's a different product. What happens if B turns into the enolate, and it reacts with A. So now what I'm saying is that this position will form the enolate. If I'm going to talk about forming an enolate at the alpha position, it takes alpha protons to do that. So if I'm talking about B being the enolate and forming the negatively charged ion, then I'm not talking about this particular set of electrons now attacking this position. Now I'm talking about a set of electrons that would form here. And that means this would attack that position. Now, just for simplicity, I'm going to keep those nice and erased. I'm going to put back my B so that folks can see that. Make my A back. And so if I make the B be the enolate, then I'm going to have the enolate that formed at that position right next to the doubly bound oxygen. And it's going to react with A in this case to form this structure. And so far that's different than all the other structures that we've listed. Now the last possibility is that B and B could react together. Having the same spot where the enolate forms, be forming in that secondary position, and it would still attack the carbonyl carbon. Oops, I think that's 1, 2, 3, 4. That's an extra one. I'd have this structure now. And this is definitely different than the previous structure or the previous 3 structures. And so we really do get 4 different products if we mix 2 different ketones or aldehydes into a pot and say, go do some aldol condensations. These are called crossed aldol reactions. And so we really want to get into this idea about how do we accomplish crossed aldol reactions. So how do I get it? How do I do this? Let's just say, for instance, that this was the one that I wanted. Let's go back. Let me make sure I'm having the senior moment. Oh, yeah, I made some mistakes here. Yep, wasn't quite a senior moment. It was an acknowledgement of some mistakes. Okay, so those were not carbonyl groups. Those are going to be OH groups. Remember, if we do a condensation, then we form a double bond between the alpha and beta position. Otherwise, it becomes a beta hydroxy ketone. And so that was my bad for having those spaces before listed as double bound carbons to oxygen. They should have been OH groups. So make sure to go back in your notes and change that if you were copying these down and making notes out of them. So I'm glad I didn't spend too much time moving along after that. Let's see what we can do then. Let's move forward. Let's go ahead and shrink this back down. Get back to where we were. I'm going to do the erasing there. And so let's think about, this is what made me think about this. What if this was the species that I wanted? What if it was this one? How do I get this to happen? Well, in general, there's 2 ways to get species that you want as the products to work in these crossed aldol reactions. One of them is the situation where one material has no alpha protons, right? Because in order to form an enolate, you have to have alpha protons. Here's an example of something that doesn't have alpha protons. So if you mix this with this guy, here's some alpha protons. And so those alpha protons would react and attack the carbonyl on the benzene, and you would get the beta hydroxy aldehyde in this case as a product. Another example of a species that doesn't have alpha protons is good old formaldehyde. So if you just want to add one carbon, you could do that with formaldehyde. But by far the majority of reactions, especially like the one that I started with by saying, what if we want this guy in the corner? The other thing that you can do is you can convert reactant to enolate first. And you would use a irreversible reagent like LDA. So we talked about that earlier and how that creates an irreversible enolate ion rather than a mixture of enolate and enol. So let's take a look at that. Let's take a look at how that would work. How could I make this by doing that? Well, if I wanted to make this species the enolate so that the carbon-carbon bond forms where this, let's go ahead and change colors. Let's make that a little bit more obvious. Let's make it blue. Go back to black. So that I form the bond between an enolate at this position attacking that carbonyl. What I can do then from a synthetic standpoint is I can mix this substance with LDA. And that will irreversibly form the enolate where I want it. Then after I do that, I can add the ethaldehyde or acetaldehyde that I want to form the reaction with. And so from that standpoint, I need some species to finish off that particular reaction. And doing it this way allows me to form the enolate between the two ions that it is that I want to form. Excuse me, make that water. And so now I have the product that I'm interested in. Now I can, I can go on with some sodium hydroxide and heat. And I can do the condensation. So that I end up with this structure. And so this is a crossed aldol reaction. And so this is how you avoid that mess of products that we were talking about before, and you end up with just the product that you're interested in. So it's not really new from a reaction standpoint. It's new from the standpoint that, hey, look, if you want an interesting product that's made from two different carbonyl species, you're going to need to think about the order that you do that in from a synthetic standpoint. Okay, the last bit about aldol reactions involves intramolecular aldol reactions. So what if I had a reagent like this? And I'm going to do sodium hydroxide and heat. Now, remember that with sodium hydroxide, it's not going to be irreversible. There's going to be an equilibrium, but the heat is going to drive it to completion because I'm going to form the conjugated system, and I don't need the stronger base in order to do that. But that means I'm going to either form enolate there, or I'm going to form an enolate there. And depending on where I form it, it depends on where it can attack. Well, it can't attack around back on itself. So if I form it there, it has to attack here. If I form it there, it has to attack there. Now, in this particular case, I created a symmetrical species on purpose so that it didn't matter which side I did that on. So let's just say that I'm going to form the enolate at this last spot here. And so that means that the enolate will react and form a bond to the other carbonyl carbon. So let's go ahead and count those atoms again. 1, 2, 3, 4, 5, 6, 7. So it's going to actually make a 7-membered ring. See if I did that right. 1, 2, 3, 4, 5, 6, 7. I did. Excellent. Let's see if I can clean it up just a little bit. One, 2, 3, 4, 5, 6, 7. Okay. So where the reaction took place and formed the double bond, and I'm only going to put the OH there temporarily just so that we can see it, that's where the attack happened. And so that means that where the attack happened, there's also, right here, there's another group there. Now, and so that means that so that means this group is attached at the alpha position. Oops, excuse me, at the beta position. And so that means there's a carbonyl group there. Now, once I've gone and done the condensation part, I'll end up with the alpha beta unsaturation like this. And so you can have an intramolecular aldol reaction to form rings. You know, it forms 5-membered rings and 6-membered rings pretty easily. It doesn't really do 3- and 4-membered rings. And then, of course, if you can do 5 and 6, you can do 7 and up as well. It's just that, remember, the most stable rings are going to be 5- and 6-membered rings. Okay. All right, so that's it for aldol reactions. And I know we did spend a lot of time talking about aldol reactions. But moving along in our carbonyl chemistry, we want to talk about a situation that's darn near analogous to an aldol reaction, and that's a Claisen condensation. So I need a base again, and I'm going to use sodium ethoxide and then a proton source. And I still form an enolate at the alpha position where there's alpha hydrogens. Except instead of forming an alcohol, I form the double bound oxygen stays in place. And so it's important to take a look at what happens here. So let's take a look at the mechanism. So what if my OR in this case is OET, and there's going to be an alpha proton there, and that alpha proton is going to form the enolate. Okay. All right. Now, that enolate can come around and react with the carbonyl group of another one of these molecules. Okay. Now, this is a pretty weird situation. It's going to be a tetrahedral intermediate. So let's take a look here. Still got this carbonyl group there. And now I've made a bond. I've made a bond here. I still have the OET, but I've also got this negatively charged oxygen and I've got that methyl group that's still there. Okay, so this is what happens at this point now. I'm going to actually just expel the OET, and that's what's going to reform the carbon-oxygen double bond at this location, leaving me with only the methyl group. All right, so now what happens? Well, recall that when we use acid with a we formed a doubly stabilized, we formed another alpha position. And so I'm getting ahead of myself. I'm going to talk about hydrolysis in a second. But what happens at this point is that the OET that we just expelled comes around and reforms another doubly stabilized enolate ion. And this is actually what drives the reaction forward. The acid hydrolysis is for this last step. We can't avoid that deprotonation, and so we have to put it in another pot to reprotonate it back to this guy. Okay, so I was getting a little bit ahead of myself because I do need to say one little thing. Why is it that we specifically used this? We can't use, or we must use, alkoxy base that matches the ester. And this is why. Let's imagine this situation. Let's imagine this situation here. If you remember that back in our carboxylic acid chapter, when we had an ester, we could do base catalyzed hydrolysis. And I can convert this thing into a carboxylic acid. Essentially what's happening is I'm replacing the OR group with the OH group. A similar reaction happens if I use an alkoxy base. But this is called transesterification. Instead of replacing the RO group with an OH group, I replace it with a different alkoxy group. And so why is this important? Because in the reaction, this is called a Claisen condensation. In the Claisen condensation, this is happening. This is happening all the time with this ester. And so if we use a different alkoxide, then we would get this transesterification happening. This is called we would get this transesterification happening at every given moment. And so what we would end up with at the end of the day would be a mix of products where this group would be an ethyl group, or it would be the other alkoxide group that was in the molecule. And so you do have to use an alkoxide base that matches the ester that you start with. Okay, so and that's Claisen condensation. It's very similar to Aldol reactions. And it's actually so similar that you still have to consider what do you do in the case of a crossed Claisen condensation. I mean, the same thing, the same idea applies with Claisen condensations as it did with Aldol reactions. There's only one of these species that has alpha hydrogen. So there's only one of those species that can form an enolate and do the Claisen condensation. And so it's this guy. This guy makes the product like that. Again, you can do intramolecular, just like you did with Albal reactions. We can do intramolecular Claisen condensations. It's just a little bit more interesting of a species. Again, this one is symmetrical. Remember that we're talking about alpha positions. So there's an alpha position there and an alpha position there. Let me actually add another carbon because I don't want to make a 4-membered ring. I want to make a 6-membered ring. So there's alpha positions here or there, in which case I would get, and here's where I was going with that, starting with that 1, 2, 3, 4, 5, a 6-membered ring. And so in this case, we would form 1, 2, 3, 4, 5, 6 members. Here was where that enolate occurred. So there was and this is the bond that was made. Okay, so there is a intramolecular Claisen condensation, just like there are intramolecular Aldol reactions, and all the considerations are exactly the same. Okay, all right. Yeah, let's get into something that's just a little bit different. Let's talk about alkylation at the alpha position. Okay, so if I take something like this and I react it with LDA, then I will irreversibly form an enolate ion. And then if I react that with Rx, then in a SN2 style reaction, that lone pair will react with that carbon, that partially positive carbon of the alkyl halide, and it will do a substitution. So this is SN2. All of the normal SN2 reaction considerations apply. Specifically, it has to be methyl or primary for the Rx. If you have tertiary, you know, that just can't do SN2. And secondary leads to too much competition. So you get the elimination product, you get a competing substitution product, and you get the alpha halogenate, you get the alpha alkylation product. So it's just too much of a mix of stuff going on there. And so we want to keep those from a synthetic point of view to a primary alkyl halide or a methyl alkyl halide. Well, what if we're going to do this same reaction where there's already an R group? And so that leaves two possibilities for our LDA application. I can form an enolate ion in the location where the first R group is already in place, or I can form an enolate ion at the other alpha position. And so what I want to do is I just want to look at their resonance structures, because the resonance structures will actually help me understand which one of these is more stable. Look what happens here. When I draw the species of the enolate ion that has the negative charge on the oxygen, I form that double bond between the carbonyl carbon and the alpha position. In this situation, it's more substituted. And in this situation, it's less substituted. So in all things being equal, the more substituted means the more stable. The less substituted means less stable. But let's take a look at what else is going on here. Which position is hindered? This position is hindered for the base to attack. It's a tertiary position, so removing that proton there is a little bit more of a problem than removing the proton there. So what do we have here? This is a competition between thermodynamics and kinetic control. This is the thermoenolate, and this is the kinetic enolate. And so which one of these forms definitely depends on the reaction conditions. That's really what's going on here. And so what does that mean? That means that if there is an alkyl group at the alpha position, when I do this alpha alkylation, I have two options. If I use a non-sterically hindered base like sodium hydride, and I do this at elevated temperatures, room temperature is fine, then I'm going to end up with the thermodynamic enolate because the base is small, so it can get in there, overcomes my steric issues, and I'm going to end up with the thermodynamic product. If I use a slightly more sterically hindered base, like LDA, and I use some really cold temperatures so that I don't have enough energy to overcome activation barriers of the reverse reactions, then the alpha halogenation happens on the other side. So it's the same reaction, but the isomeric results are different based on the conditions of the reaction. And so we've seen this play out a bunch of times this semester. And so we're seeing this play out yet again. Again, it's kinetic versus thermodynamic control, whether or not you have steric considerations or thermodynamic considerations, sterics leading to faster products. So least sterically hindered means that the lower activation barrier, that's the kinetic product, or the thermodynamic consideration, which would mean the more substituted enolate ion, and the more substituted enolate ion is the thermodynamic enolate, and leads to the alkylation happening at the same position as that other alkyl group was attached. So there's two different considerations to be made with those reactions. All right, so that's really it for alpha halogenation, or excuse me, alpha alkylation. So what I want to move on to now are two similar reactions called the malonic Ester synthesis and the acetoacetic ester synthesis reactions. And so this is malonic ester. It's a doubly it'll form doubly stabilized enolate ions very easily. And so if I react this thing with some sodium ethoxide, again, still avoiding transesterification, and I react it with an alkyl halide, some acid and some heat. What do we get? Oops, this is not a H, this is an ET. What do we get? We get a carboxylic acid that has an R group added at the alpha position. Okay, so let's take a look at how this happens. So recall that there are some hydrogens here. And so the sodium ethoxide will remove one of those hydrogens. And it'll form this enolate ion. And again, this is a doubly stabilized enolate ion. And so this happens irreversibly, essentially irreversibly. And so now what do I have going on? So now I am able to react this guy in that SN2 reaction. To alpha halogenation like we saw before. Okay, so this was step 1. This one was step 2, and I'm going back to my reaction sequence up here. Well, what's going on with step 3? Well, recall that from our carboxylic acid section where we were talking about esters, if I have a hydronium ion present in the reaction, then I can do acid catalyzed hydrolysis. Now I'm going to draw it this way to be consistent, but remember that this is a single bond and that there is free rotation around that single bond. So I'm just going to draw this again after a rotation. And I'm going to show you how we end up with carboxylic acid on one side and not the other. So now I've got double bond here and OH here. Okay, we get some really, really fun stuff that's going on here. Let's take a look at how this works. That guy can grab that. This guy can make a double bond here. And that guy can react with this. And what do we get then? What's going to happen right there? Well, that's going to be CO2, and that CO2 is going to leave the reaction. And so that's what's driving this forward. So I'll still have an OH here. I'll now have this OH group on that oxygen and this R group. What's this? This is an enol. And what's going to happen to the enol? It's going to tautomerize into a ketone. And we have already seen, or it's going to tautomerize into an alcohol, excuse me, a carbonyl group. And we've already seen how that works several times. So that's what's happening with malonic ester synthesis. So we can get this, we can take this malonic ester and we can react it with a suitable base and an alkyl halide, and we get alpha halogenation. But we're going to lose part of that ester through decarboxylation. This step is called decarboxylation. And we're going to end up with ultimately a carboxylic acid because the enol is going to tautomerize. The enol that forms from the decarboxylation will tautomerize into the carboxylic acid. Okay, you can also do this twice though. So let's take a look at that real quick. Just take a look at that. Let's just change this reaction sequence up just a little bit. So malonic ester. Sodium ethoxide. RX, but then let's do that again with sodium ethoxide and let's make it a different R prime X, and then let's finish that off with the hydrolysis that leads to decarboxylation. I still end up with a carboxylic acid, but in this case, the carboxylic acid has two R groups, R and R prime. So you can do the alkylation twice, depending on the conditions of the reaction or the reaction sequence that you use. So that's an important consideration to think about, whether or not you've added two R groups at the alpha position or just one R group at the alpha position. A similar reaction to malonic ester synthesis is acetoacetic ester synthesis. So it involves a similar type of species. It does have ETOH on one side, but it doesn't have ETOH on the other side. Now, I can still react it with sodium ethoxide to form a enolate ion that's doubly stabilized in that location. I can react it with alkyl halide. I can do the same exact decarboxylation step on, it'll have to be over here though. So what do I end up with? So instead of a carboxylic acid, I get a ketone. So what did I effectively do here? I took this R group, I took this R group and I added 3 carbons and a carbonyl group to the end. I added a 3-carbon ketone to the end of this R group. So from the perspective of the R group, what did I do? Let's write it from that perspective. I did that. So it's the same reactant or the same product, just a different perspective. And so keep in mind, I can show this from you from the acetoacetic ester perspective, or going back to the other one, I could show it to you from the malonic esters perspective, or I could show it to you from the perspective of the alkyl halide. In either case, we're talking about the same reaction leading to the same products. So again, just like the other reaction, going back to the acetoacetic acid acetoacetic ester perspective, I can do this series of reactions twice. A different alkyl halide this time. And I end up with the same 3-carbon addition onto, but now instead of onto one R group, I've connected those 3-carbon ketone to 2 R groups at the same time. So again, just like the other one, the malonic ester synthesis, we can do this stepwise so that we get 2 alkylations happening at the alpha position. All right, so some more alpha additions would involve using a Aldol condensation product. And the reason it involves an Aldol condensation product is that we can show that the Aldol condensation product, through some resonance, has quite a bit of positive charge at the beta position. And so that means that for this species, there's a partially positive carbon charge there. Now, there's also clearly a partial positive charge at the carbonyl carbon. And so you can get alkylations at both locations. And so in fact, it really does depend on the reactant that's involved. If you do Grignard, then Grignard does prefer to react at the carbonyl carbon. And that double bond stays intact. But if you use Gilman reagent, R2CuLi and acid workup, you get alkylation at the beta position. Okay, so these are called Michael reactions. Where we get addition at the beta position. It's really called conjugate addition because keep in mind that in addition to Michael addition, it's called conjugate addition because keep in mind that these bonds are conjugated. We saw this happen with conjugated dienes. Same thing is happening here. It does look like here's a hydrogen, here's 2 hydrogens. It looks like it's 1,4 addition, or 1,2 addition, but it really is 1,4 addition because what you're going through is this intermediate, and I'm going straight from there or straight from here. Either one of those will work to get the R group added there. And when you add the OH there, that's an enol, so it's going to tautomerize to a ketone. So there's some tautomerization that's happening in the process, and that's why it's actually back it up, 1,4 addition, and not the 1,2 addition as it looks like in the conjugated system. Okay. All right. So what happens if we start with a for a Michael reaction? What happens if we start with a doubly stabilized enolate? The doubly stabilized enolate has its own name, and these are called Michael donors. These are called Michael donors. And so if I react this with a species like this, of course I had to react the parent species with sodium hydroxide to make the enolate. This thing is called a Michael acceptor. So what do I get? I get the carbonyl group, and I get a new carbon-carbon bond that forms. It's going to form at this beta position. And the ketone stays in place. So this is the product that I get, and this is called a Michael reaction, a Michael addition. Now there's lots of Michael donors, and there's lots of Michael acceptors, and you really do need to become familiar with them because they're going to be able to do any combination will be able to do this type of reaction. So any combination of donor and acceptor can do this reaction. So I'm going to show you 6 donors and 6 acceptors. And so that leads to quite a few different permutations of combinations. So let's take a look. Here's one Michael acceptor. I'm going to go ahead and write their enolate forms. We talked about that one. So it could also be acetoacetic ester. It could be malonic ester. It could be, here's one that's also resonance stabilized, although it might not be easy to see at first. Could be this guy. Could be this guy, is also resonance stabilized, hard to see at first. And then finally, it could be a Gilman reagent. What are Michael acceptors? Well, we talked about just a regular old Aldol condensation product. It could have an aldehyde on one end. It could have a ketone on one end. That's going to be fine as well. What else could it have? Well, it could be an ester. It could be an amide. That would work. Could be a nitrile. That'll work. And it could be NO2 as well. And all of these things have in common that there's partially positive carbons at the beta position. And when reacting with all of these Michael acceptors, they're going to form carbon-carbon bonds at the beta position. Okay, well, what if you wanted to do this reaction, the same type of reaction, But what if you wanted to do it with something that wasn't doubly stabilized? So even if I were to use a strong base to irreversibly form an enolate ion, it turns out that we really just don't get a whole lot of what we would think of as the Michael addition product. This is really just not formed. Well, we can turn this type of ketone, we can turn a ketone into an acceptable Michael donor so that we can do this reaction. And this is called the Stork enamine synthesis. Here comes that enamine roaring back to you. Recall that we can take a ketone, and if we react it with a secondary amine with H plus catalyst, and we remove some water, that we can form, an enamine. So there's a double bond here. Well, let's take a look at this enamine. Well, there's a lone pair here, and I can show you a resonance structure where I've got this nice lone pair at this essentially what I'm going to call an alpha position. And so this is a Michael donor. And so it can react with this species. And form this guy. So here's something that looks a lot like an iminium ion. There's iminium ions back at you. So here's the iminium ion. And here's the enolate ion over here. And what happens if we take both of these things and we react them with some acid? Well, we know that the iminium ion will reform a carbonyl group, and the enolate will form an enol, and the enol will tautomerize back to a ketone. So now what do we have? So if we have a much more complicated process, but we can take something like this that's not a Michael donor, and we can turn it into a resonance stabilized enolate type of ion through reacting it with a secondary amine in good old enamine formation. So once it's an enamine, we can show that resonance stabilized pair of electrons. Let's get some more room here. We can show the resonance stabilized pair of electrons on the enamine, and then we can take the enamine and react it with the Aldol condensation product, the intermediate of which would be a combination of an iminium ion and an enol, and then we can hydrolyze both of them back into ketones, and we form a diketone. So that's actually a pretty handy synthesis. Okay. Couple of other things. Actually, just one more thing. Let's do this same thing. Let me show you a pretty handy reaction called the Robinson Annulation. Annulation means to form a ring. So what if I take a doubly stabilized, or something that has the potential to form a doubly stabilized enolate, but I give it another R group there. What do we get? So what happens if I mix it with sodium hydroxide? Well, we know that in the first situation, we're going to get Michael addition. So I'm going to form a bond there. We've still got this doubly bound oxygen. So this is the Michael addition. Then, in the presence of sodium hydroxide, I can have an Aldol condensation. Because here's an opportunity for an enolate to form there and react with this carbonyl there. And so what do I get? Here's this first ring. Now I've made another ring. There's still an R group there. And so this is the Robinson Annulation. Which means to form a ring. Woo, that's a lot of chemistry. That's a lot of alpha carbon chemistry. And so I'm going to leave it there. That's it for the day. What we're going to get into coming up next, the very last section, is amines. And then once we do amines, we're done with organic chemistry too, as far as I'm concerned. You can certainly have a larger conversation about polymers, and there's a lot of other topics like carbohydrates you can get into, but I'm not going to get into those at this time, not in this particular course. So we'll come in and we'll do some problems the next time I see you guys, and hopefully you have watched this video. So good luck.